Yeah, Ashley, I think we will start now.
Yes, sir. The capacity to learn is a gift. The ability to learn is a skill. The willingness to learn is a choice. Good morning, galaxy of intellectuals, resource person, Dean Ycet, HOD of Electrical Department, faculty members, and participants. On the third day of Faculty Development Program on Clean and Green Energy for Sustainable Development, we welcome you all in the gathering. It is a matter of great happiness to welcome you all in the Faculty Development Program organized by the Department of Electrical Engineering, YCT Jammu. Success waits patiently for anyone who has the determination and strength to seize it. Sustainable development is a process which enables all people to realize their potential and to improve their quality of life in ways which protects and enhances the Earth's life support systems. Keeping this in mind, department has organized a faculty development program on clean and sustainable development. Now, I would like to invite the HOD of Electrical Department, YCT, Engineer Lavnish Talwar, for the welcome address.
Thank you, Ashley. It is audible.
Yes, sir.
Okay, thank you so much. Respected worthy speaker of the day, Chief Coordinator YCT Engineer B.R. Verma sir, Dean YCT Engineer Dinesh Gupta sir, heads of the departments, the faculty members of Electrical Engineering Department, and most important, all the participants for today's event. A very good morning to all to be present here. It's an immense pleasure for me on today to formally welcome the resource person for the third day faculty development program on clean and green energy for sustainable development organized by the Department of Electrical Engineering from 25th 1 to 25th of February 2022. And today our resource person is Dr. Sanjeev Anand, Assistant Professor, School of Energy Management, Shri Mata Vaishno Devi University, KATRA. Before handing over the entire platform to the Dr. Sanjeev Anand, let me introduce to all with Dr. Anand. Dr. Sanjeev Anand is presently working as an Assistant Professor, School of Energy Management, Shri Mata Vaishno Devi University, KATRA. He received his BE degree in Mechanical Engineering in 1995 from Nagpur University, followed by MTech degree and PhD degree both in Energy Management from Shri Mata Vaishno Devi University. His area of interest is energy efficiency, heat and mass transfer, energy exergy analysis. He has published more than 30 research papers in international journals, and moreover, he is the author and the co-author of 4 reputed books. In addition to that, he had also attended more than 20 national as well as international conferences organized by the various institutions as well as universities. He has supervised 3 research projects, out of which one project is awarded, one is submitted, and another is in process. He is a certified marine chief engineer given by Maritime and the Coast Guard Agency, United Kingdom in the year 2007. He is a life member of many organizations such as Solar Energy Society of India, member of Indian Society of Heating, Refrigeration and Air Conditioner, ASHRI, and moreover. One thing that I will tell you all about Dr. Anand is a great man of great visionary, and he always tried to help their students, researchers and fellow in the field of energy management. It is a great pleasure for me, and I am very glad and grateful and proudly announce that I am a student of Dr. Anand. Under his supervision, I completed my MTech degree in the year 2009. He has a very rich experience in the field of heating, cooling and ventilation system, and also that are used in the field of energy management. Today, he will deliver a talk on thermal selective coatings and its enhancement characteristics for efficient power generation, PTC. I hope you all get benefited from this lecture. Thank you so much. Over to Esli.
Thank you very much, sir, for your kind words. I would now like to invite the resource person for the third day of Faculty Development Program, Dr. Sanjeev Anand, Assistant Professor, School of Energy Management, SMVDU, KATRA, Jammu, to conduct the session on thermal selective coatings and its enhancement characteristics for efficient power generation through parabolic trough collector.
Thanks. Am I audible to all?
Yes, sir, you're audible.
Am I audible?
Yes, sir. Yes, sir. You are audible, sir.
Yeah. Okay. Thanks inviting me for delivering the lecture. First of all, I would extend my thanks to Vidhi Singh ji. Uh, Basically, he's one of the person who is very much known for enhancing the technical education in the Union Territory of Jammu and Kashmir. And I was basically fortunate enough that I have a very brief stint of my career with his group also. That was very a short period for around, I think, 3-4 months. But even that 3-4 months was basically a very good time we spent. And I was present in the inaugural session for a short time because there was some emergency which I apologize for the same. And I basically am very thankful to Professor Rajnikant, Professor Pavnish Abrol, uh, who were there as the chief guest and the guest of honor. And they are very renowned persons in their field as far as the academic arena is concerned in the Union Territory of Jammu and Kashmir. I would like to thank Lavnish for giving me this opportunity to uh, deliver a talk on the various aspects which have been carrying forward uh, for improving the energy efficiency concerns in the area of Jammu and Kashmir and the world over. And we basically try to enhance some of the things and we try to get the document published in some of the reputed journals. Uh, of course, everything happens with the support of the brilliant students which we have with us. And what I will be presenting today is also basically what I am guiding to one of my student who is already doing a PhD program. And this is the area which we are enhancing as far as the power efficiency is concerned in case of the parabolic trough collectors. So when we glance through the uh, presentations, we will see that what is the level of work that student is being doing. Also, it looks very, it gives a very healthy feeling when you see that two of your students, Lavnish and Azli, they are part of this faculty development program, and they have organized it very, very well. And also one of my colleague, my, you can say a PhD student, he has already delivered a lecture on building applications, the energy efficiency in building on the very first day. So it gives immense pleasure when you see the academics is really growing, and you see that the students, they are doing really well. Uh, so, Lavnish, I have to share the screen again.
Yes, sir. Yes, sir.
So is it visible to all?
Yes, sir, it is visible now.
Okay. Now, the today's talk is basically on thermal selective coating and its enhancement characteristics for efficient power generation through parabolic trough collector. Now, if we go by the theme of the faculty development program, it's basically a clean and a green energy for sustainable development. And I take a word from the inaugural address of Professor Rajnikant, where he spoke that the green energy or a clean energy is basically less visible on the ground, as it is basically being shared on the literature or on the books. And to some extent I do agree with him, because that particular thing is because of the lack of awareness among the people, and also the policies which our government make. So those policies, they are not basically disseminated to the users or the people who should get benefit on that. So that is why we see that the extent of the generation which is should be there from the renewable energy, that is basically not present. But we have done tremendously very well in the few years, in the previous few years, where the generation levels, they have very gone up. Now when I go through this particular slide, I will be discussing on the various aspects that how we can enhance the power generation using the parabolic trough collectors. Now these are the basic contents of my presentation. I have the introduction section, then we will be discussing on concentrating solar collectors, the parabolic trough collector, how the steam generation it happens, heat transfer fluid and its advancements, absorber tube and advancements, selective coating methods and characterization. Then we have conclusion and references. Now, if you see this particular, the parabolic trough collector is one of the matured and it's a feasible technology used for various low temperature applications and medium to high temperature thermal applications. Various advancements in the field of PTC technology will be discussed in detail throughout this presentation. The study reviews nanoparticle-based heat transfer fluids and selective coatings. This work will enable us to understand the parabolic turf collector systems along with latest advancements in the field. Now, when we talk about the concentrating solar collectors, a concentrating solar collector is a solar collector that uses reflective surfaces to concentrate radiation onto a receiver or absorber, which converts it into heat from various applications. The concentrating surfaces can be reflector, refractors, cylindrical, or can be continuous or segmented, while absorbers, receivers can be convex, flat, or concave, and can be covered or uncovered. The main factors affecting the mobility of the concentrated collectors is the concentration ratio, which can be defined as a ratio of collector aperture area to the absorber area. Concentrating collectors are divided into two groups: non-imaging collectors with low concentration ratio and linear imaging collectors with intermediate. Now, concentration ratios can be varied from less than unity to high exponential values of the order of 10 raised to power 5. Increasing ratio means increasing temperatures at which energy can be delivered. Now, the extent of this particular concentrating solar collectors, like why we are discussing on these particular aspects, is that if we see the power industry is basically looking for the lower emissions, and if we have to see that the emissions has to be reduced, we need to have the more energy efficient conventional systems, or then we will have to adopt to the what is called as this renewable energy systems, where we can concentrate the solar radiation, increase the their capacity, and then we have to produce the steam, where the steam will be used for expanding in the turbines, and we'll be producing the power like the same what is being used in a coal fired power plant. Now the extent to what we are discussing is basically concentrated to one area, because you see, if I talk about power generation using renewable, I'll be using the help of the people who are from the electrical background. I'll be needing help from the people who are from the mechanical background. I'll be needing help from the people who are from civil background also. So The energy sector is basically an interdisciplinary area where we need help of each and every person from their particular expertise to arrive at such a situations where we give justification to the theme of this FDP, that we have to generate a clean energy and then we have to have a sustainable development. Now this particular slide, you see we have a different type of concentrating solar collectors. We have a parabolic trough, we have a linear Fresnel reflector, the parabolic dish, and we have a central receiver or a solar tower which is there. So this is like the very basic aspects which are being followed for the concentrated solar collectors, and they are being used for a wide variety of applications, right from high medium temperature applications. Now this is another, you will see that the solar thermal, it's a Schaeffler dish, widely used for solar cooking applications. If you happen to see, there is a solar cooking applications. We have a lot of dishes which are being used in Shirdi, where the food is being cooked using these particular Schaeffler dishes, and they have automatic tracking also, which is basically being used, and the maximum percentage of solar radiation, they are basically concentrated, and the heat is transmitted for cooking the food. Now these are some of the design equations, very useful equations which we are using for the design of a solar concentrating solar collectors, and they can be optimized by calculating the thermal losses. We have a collector efficiency factor which gives you the various factors like the overall heat transfer, the diameter. Then we have a heat transfer coefficients which are being used. Now when we design a particular collector, we need the help of a person who is conversant with the heat transfer principles. And that is why he will be utilizing these particular equations, the design data, and then he will be calculating what is called as the particular area which is required for a particular collector, so that we can produce a certain amount of a heat which is required for the power generation. Then another, we use a loss coefficient, that is, and a collector heat removal factor. These are some of the important, very important design equations which are used for designing these particular collectors. Another one is the collector useful gain, that is QU. We have the efficiency factor again. We have taken into account what is called as a transmissivity and absorptivity of the particular surfaces also. Now, a parabolic trough collector is a linear solar collector which concentrates the solar radiation onto a receiver tube. Some of the key features of PTC are: the incident rays are concentrated on receiver absorber with the help of parabolic reflector. Heat transfer fluid is continuously made to flow through the absorber tube, which produces high temperature steam. Steam can be produced either via direct steam generation method or via indirect steam generation method. Parabolic trough collector PTC system can achieve temperature ranging from 80 degree to 550 degree centigrade. This is another picture. If you see, that is a parabolic trough collector. So we have an absorber pipe which is going through the axis. We have a borosilicate glass envelope is there on the pipe, so that whatever heat which is being entering, so that will be transmitted to this, the fluid which is entering this particular pipe. The radiation, they will fall on this particular curved surface. They will be reflected back, the concentrated air, and then we have a high temperature fluid which is passing through this particular tubes. They will be heated up, and accordingly we will get what is the desired amount of a heat. Now if you see this particular thermal circuit diagram of a PTC receiver, we have radiation. One is this is basically resistance in series, and we have a parallel combination here. The electrical people, they are very conversant with this type of arrangements. So we have a radiation here happening. We this is a conduction part. This is radiation and convection which is taking place. And then we have a different terminologies like the receiver temperature, outside cover temperature, sky temperature, inside cover temperature, and the ambient temperature. So this will give us the overall heat which is being transmitted to the fluid by different modes of heat transfer, that is radiation, conduction, and convection. Then we have the collector losses in a PTC receiver tube. We have a radiation losses, which is given by this particular equation. We have conduction losses. Then we have convection and radiation losses. So these three important aspects, that is radiation, conduction, and convection, these are very, very important aspects as far as the heat transfer is concerned. In case of a renewable energy applications, or even in case of a conventional systems also, where these particular design equations are to be used for designing the particular system. Now, steam generation. We have indirect steam generation. As the name suggests, the steam is produced indirectly through mutual heat interactions between a high temperature fluid or oil and water in a suitable heat exchanger, as shown is figure in the further slides. We will see that. The direct steam generation, this mode of steam generation converts the water flowing inside the receiver tube directly into high temperature steam due to high concentration of solar radiation over the receiver tube. Now, if we talk about this particular indirect steam generation, now let me elaborate on this further. Like when we are using a conventional heating systems, like for example, if we are using a conventional coal-fired thermal power plant, what we are using is we are burning coal in a boiler, and what we have in boiler, there is a water. That water takes up heat from the combustion of the coal, that the heat will be transmitted through the surfaces, and the water is converted into the steam. And further, if we go on heating, that particular steam will be converted into a superheated steam, and that will go and that will be expanded in a turbine for the generation of power. However, in case of a direct steam generation, what we have seen the previous slide about the parabolic trough collector, you see that we have a receiver tube where the water is there, and then when we are concentrating the solar radiations, there continuous transfer of heat take place, and that water is slowly converted into the steam. That is, the phase is being changed directly there. So there is no indirect, there is basically a direct system. However, here we have a suitable heat exchanger where the heat transfer is taking place. Now this is a indirect steam generation system in a parabolic trough collector power plant. You'll see we have solar field, we have these collectors there, all of these connected, they are connected. After that, we have these two particular tanks. This is a heat exchanger. So what is happening is that when we are sending a fluid from here, so the heat will be given to this fluid, and the fluid will be coming after that. What is happening is that when we take another fluid, we are basically transferring, we are forming a steam here. Okay, and then we have, this is a particular phase change material, that is thermal storage is there, where the heat from the sun, it is being stored. Why it is being stored? Because we have the sun only in the daytime, and after that we need a heat for a continuous supply to the turbine. So then we are using this particular heat exchanger for the generation of steam. This is your steam turbine where the high temperature steam is being expanded. And after that, it is basically running an alternator where the power is being generated and it is transmitted through the transmission lines uh, to the distribution systems towards the buildings. However, whatever is being rejected from the turbine is again, it is getting cooled in a cooling tower, and we have a closed cycle where the resources are not being wasted, the water is not being wasted. However, if there are any leakages, then that will be taken care by using the makeup water. However, it is basically a closed system which is working, and mostly all the thermal power plants, they work in a closed cycle only. Now this, sorry. Now this you see, this is a steam generation. We have a solar collector is there. This is a parabolic collector. We have a storage tank, and we have a pump through which we are basically moving this fluid in these particular receiver tubes, and after that it is going to the other tube and then it is coming back. And you see that in direct steam generation, showing inside the absorber tube, you see that how the phase is getting changed. We have a single phase water, then there is a nucleate boiling, that is small bubbles are being formed. After that there is convection boiling, and we get a dry steam after that. This is here when x, we say x is equal to 0, that means the dryness fraction is 0, that means it is full liquid. Where x is equal to 1, the dryness fraction is 1, so that we have a totally dry steam which is coming after this. And why we need a dry steam is that because you see that these steam turbines, they are basically rotating at very high speeds. When I say high speeds, that means if the order of more than 10,000, 15,000, maybe 20,000 RPMs. And if we uh, don't provide the dry steam, any wet steam which is coming inside that particular turbine blade, then the momentum will be such that of that particular water droplets, it will break the turbine blade. So it is very, very dangerous. The wet steam is very, very dangerous for the turbine blades. So they will create pitting marks, or even they do the blade damage if the wet steam is provided during the turbine running. So that is why we need a dry steam, or we need a superheated steam for the efficient power generation and reliability of the equipment. Now the heat transfer fluid used in the receiver is responsible for generation of high temperature fluid. However, it is necessary that heat transfer fluids should be selected on the basis of their heat exchange rate and high thermal stability. So that is very, very important, that whatever the heat transfer fluid we choose, that particular heat transfer fluid should be selected on the basis of heat exchange rate and high thermal stability, because these two parameters will decide on what is the life of this particular heat transfer fluid. So some of the commonly used thermal fluids, they are synthetic thermal oils, that is Therminol VP1, Therminol D12, Dowtherm A, Slytherm 800 are used as heat transfer fluid due to their high thermal stability. That means they are basically stable even at high temperatures. No doubt, these thermal fluids have different working temperatures. Now, the molten salts like eutectic salts, high-tech solar salt, nitrate salts, and carbonate salts are preferable to be used as high temperature fluid, as these offer better density and stability at their respective working range. Now, the advancements in the heat transfer fluids, that is HTFs, the thermal oils and the other heat transfer fluids used in the PTC systems are result in enhanced heat transfer. Still, heat transfer fluid properties can be enhanced further by mixing the base fluid with the nano-sized additives. This process modifies the thermophysical properties of fluid and helps in maximum heat gain. Some of the thermal fluids are silver titanium dioxide, nanoparticle based quoted as 19.7 nanometer and 2.2 nanometer respectively. Various materials like iron oxide, copper oxide, titanium dioxide, aluminum oxide, zinc oxide, and silicon oxides are commonly used nanomaterials in the thermal fluid for enhancing heat transfer between the fluid and absorber tubes. Now, see, over the period of time, there has been many uh, areas where the research is basically progressing further, because to augment the heat transfer rate, so we need to add some of the like additive particle like a nanoparticles, so that the thermophysical properties of the fluid, they will change, and they will basically help in uh, increasing the heat transfer capacity of that particular fluid. Now this, you see the heat transfer fluid and its advancements. We have very thorough literature review, uh, where we see that we have like terminal VP1, slitherm, nitrate salt, and high-tech Excel, synthetic oil. Then we have again the terminal D12, mineral thermal oil, terminal VP1. Now, over the period of time, what advancement have been used? So we add aluminum oxide, then multi-watt carbon nano tubes, then copper nanoparticles. Now the outcomes, uh, what has been achieved by using these advancements have been like a better receiver performance is reported in LS2 type PTC when the vacuum is provided inside the cover. We have an increase in the Nusselt number. Uh, it has been reported while using terminal VP1 and slitherm 800 with increase inlet high temperature fluid temperature. The friction factor is reported to drop while using oils as well as in the salts. Now see, what is the idea of doing this particular literature review? The idea is that we know that what the previous researchers they have done, what type of heat transfer fluids they have used, what advancement they have used, and what claims they have made, that is the outcomes which they have shown, what is the claims they have made, and are those claims logical, and if they are logical, that how these particular aspects they can be further enhanced, and which forms the basis for the future research also. That is the idea why the literature has to be reviewed. Now we have the techniques which have been used. So these are finite volume method, that is, and another is the Monte Carlo ray trace method. So these type of different techniques has been used to evaluate the performance of these high temperature fluids, so that they can be very well used in a parabolic trough collector or concentrating solar collector for increasing the efficiency and for the efficient power generation. Now this is, you see, again we have another slide which shows the different type of heat transfer fluids that they have been taken by the other authors, and again they have shown what outcomes they have observed when they have been using the high temperature fluids, and the advancements they have been using, the different methods which they have used, like X-ray analysis or differential scanning calorimeter, and we have a TGA, MCRT, FVM, and these type of techniques, they help us to arrive at a particular solutions where we can develop our own coatings, and those coatings will be used for the efficient power generations. Now this, you see, we have a heat collection element absorber receiver. Okay, now heat transfer fluid is made to flow through the heat collection element or absorber, which further produces the high temperature steam. So this is through which we are using a heat transfer fluid. So we have a copper inside, which is backed by steel. Like it is a dual material. Like both the material, they are bonded together. These absorber tubes are generally made of stainless steel, copper, or it can be made from alloy material as per the requirement and economic involved in the system. So when I say the economics involved in the system, that is a very, very important criteria as far as the renewable energy application is concerned. Because you see that one of the reason, if we say that why the renewable energy aspects has not picked up much at the ground level, is also that uh, everyone wants that how what will be the cost of the generation if I use renewable energy, and what is the cost of the power which I am getting from the grid. So all these economics, they have to be basically found out, they have to be shared, they have to be seen that whether the equipment or a system which we are making, is it economically viable or not. Because see, at research level, at the laboratory level, so you cannot basically virtually see on the economic aspect, because there you are basically developing new systems, and those systems over the period of time, when they are tried and tested, when you are coming to the prototype stage, then you see that if I produce such a level system actually for the society, how much it will cost to us. So that is very, very important criteria. So generally it is cylindrical in shape, but some researchers have studied modified receiver tubes as stated in the forthcoming slides. Figure shows a compound absorber tube with a combination of two material, copper and a steel layered together. Now we have modifications in heat collection, or we can say absorber. We have different modifications have been suggested by many researchers, and inclusion of insert inside the receiver tube is one of such modifications. Following are some of the suggested inserts. We have inserted porous disc, converging diverging tube, pin fin inserts, vortex generator in the receiver or heat collection element, inserting a metal foam, multi-fin array receiver, asymmetric convex corrugated heat collection element receiver tube. Now, all these aspects which I have enumerated here, all these basically will enhance the heat transfer rate. So that is why we basically use this particular thing, because whatever the energy which is coming from the sun, that energy from the sun, that has to be concentrated, that has to be efficiently transferred to the fluid, so that we can produce a required amount of the uh, level at which the heat transfer fluid has to be brought, so that it is suitable for the generation of the power. So that is why we use these particular aspects for the enhancement of the heat transfer rate. Now see modification in the heat collection element absorber. You see we have a porous ring which is inserted for the absorber tube. It looks like this. We have a porous, it is inserted inside. So what will happen is that when the fluid will flow, it will basically increase the surface area contact, and then accordingly we have a increased in the heat transfer rate. Similarly, we have a converging diverging section. You see the flow is happening like this. When we are converging diverging section, what will be happening is that there will be change in the velocity of the flow, and accordingly the velocity and the pressure, they will change, and accordingly we get the heat transfer rate will be enhanced accordingly. So that is why these particular sections are being used. Now this is pin fin model inserted in the receiver tube. Like we have a receiver tube and we have these pin fins. Now these particular fins, they are also called as extended surfaces. Now these extended surfaces, these are basically used for augmenting the heat transfer rate. So once they will augment the heat transfer rate by virtue of the increased in again the surface area, because when you have increased this particular fin, the surface area is increased, so the more area will be there for the transfer of the heat, and hence the efficiency of the system will increase. Now selective coatings. A selective coating is a thin film which aids in better performance of the system while reducing losses. Some of the desired properties of selective coatings are minimum emissivity, maximum absorptivity, and stability at elevated temperature. So this is very, very important. Stability at elevated temperature is very important, because if the coating is not stable at elevated temperature, then what will happen is that the moment there is the increase in the heat transfer rate, what will happen? There will be a cracking of this particular coating. And once the cracking of this coating take place, then the overall efficiency of the system drops. So now, in addition, selective coating should be economically viable, durable, and must also possess good adhesion, transmutation, and minimum hazardous emissions. So that is also very, very important, that there should be minimum hazardous emissions, because you see that uh, in the context of making like a renewable energy or a clean energy, if these particular efficiency enhancement systems, they are hazardous, then there is no point in having this particular clean energy. So that is why this is a main criteria, that we should have a minimum hazardous emissions. Now selective coating can be divided into three basic classifications. We have metal to metal combinations, a metal and metal oxide combination, metal ceramic combination, also called cermets. A long-term thermal stability of solar selective coating in vacuum and in air is a topic of concern for few decades now. And that was basically the reason why we have a elaborated literature review on solar selective coatings. And presently, what we are working on is, we are working on developing a new coating. We have already developed one coating, and we are under testing of that. Testing of that coating is basically going on through different mediums. And once we arrive at certain amount of a result, I will be happy to share with you all about the performance of that particular coating. So these coatings are meant to increase the absorptivity of the receiver tube and encapsulate maximum possible solar flux. Considering the higher thermal stability and the lower thermal emittance, there are many solar selective coatings available. Now these are the nature of various coatings, you see, which are already available. So we have the combination of aluminum oxide, then we have the annealing. You can see the annealing temperature they have given is 580 degree for how much time, and we have the absorptivity level is there, then emissivity level, and the efficiency which is there. So these are the different coatings which are available in the market. And uh, the new coatings which are basically being formed, they are the combination or a mixture of some of these compounds only, and thereby they have a different working temperatures, a different absorptivities, different emissivity, and the efficiency rates. So this is another slide which shows the different types of coatings again. Now we have the different optical characterization tools, that how the characterization of these coatings is being done. The optical performance of absorbers can be characterized by a number of techniques explained below. One is the scanning electron microscope. Now the SEM is a widely used instrument. It is used for analyzing the profile of the coating surface with the help of a beam of electrons focused on sample, causing secondary electrons to backscatter. It detects the secondary electrons and a topographic image is produced on the screen with the help of cathode ray tube. Now, this particular SEM is basically widely used in material applications, and the coating which I am talking about is also one such material. That is why we have to study the morphology of these particular coating using these techniques. The another one is a transmission electron microscopy, that is TEM. It differs from SEM as the electron beam generated from TEM is of much high acceleration than that interacts with the sample and produces a magnified image on the fluorescent screen. TEM images has high resolution and are capable of imaging even a single atom. Then we have a pulsed photoradiometry technique. This technique is based upon the photothermal effect, which evaluates the thermal physical changes in the properties of selective coating. It characterizes the heat transport that takes place through conduction or diffusion between the substrate and the coating. Then XRD, it is a non-destructive analysis capable of measuring structural properties of material. X-rays are passed through a clean and finely finished sample. These rays form a diffraction pattern due to their interaction with the crystal lattice, resulting in the formation of intensity peaks, and thus the structural properties are evaluated. The Fourier transform infrared spectroscopy, that is FTIR, is one of the classical spectroscopy techniques that can easily characterize thin films in terms of composition, structure, stability of the compound by measuring light particle interference. This technique is also capable of checking the crystallographic orientation and order of sample surface. Then we have F10RT spectroscopy. F10RT spectroscopy is used for measuring reflectivity and transmissivity index of coating layer. This process involves measurement of light reflected from the film surface and its comparison with the pre-calculated reflectance spectra. Now these pictures, they show the morphology of various coatings. You can see that surface morphology of films of stainless steel substrate coated with ferric oxide, molybdenum and aluminum oxide coating. One is before, that is, and after heat treatment at 800 degrees centigrade for 5 hours. You see that how the lattice, that is the crystal lattice, they change after having the substrate coating and after the heat treatment of 800 degrees centigrade for 5 hours. There's the changes which are happening. So this studies will help that what will be the reliability of the coatings when they will be used for high temperature applications. Now this is morphology of various coatings we have as deposited. This is heat treated at 500 degrees centigrade for 80 hours. And this is heat treated at 500 degrees centigrade for 300 hours. So after aging at 500 degrees centigrade for 300 hours in vacuum, the values of absorptance and emittance at 80 degrees centigrade have changed from 0.95 to 0.92, and for emittance it is 0.08 to 0.10, while the surface roughness has increased. You see that the surface roughness has increased when we are undergoing the heat transfer. So it will depend upon that what is the impact of heat which is happening on the coating over the period of its usage. Now SEM image of cobalt copper manganese oxide spinel ceramic film. This coating is reported to have 0.906 absorptivity and 0.116 emissivity. The shown image illustrates grooves and pores that play an important role in light trapping. So accordingly, you will see that these morphology will tell us what is, again, I am telling you that all these things will tell us that what is the reliability and how the coating will perform when put under different temperature conditions. Now, coating deposition methods. In order to make a surface more absorptive, it is necessary to apply some absorptive selective coatings over it. Such a process is called deposition technique, and it can be done by a number of techniques explained below. One is the evaporation technique. The coating material is made to evaporate and vapors are condensed over the substrate, either by electron beam method or thermal evaporation. In order to reduce the uneven deposition and composition of the coating, it is necessary that the process should be done very rapidly as flash evaporation. Sputtering. Particles are extracted from the coating material by means of heavy ionic bombardment. Inert gas ions are used for bombardment, which transmit energy and momentum to the target atom. During bombarding of the target, the atoms from the target are scattered backward due to the momentum and energy transmission. This phenomena is called sputtering. The substrate is placed near to the target so that the extracted particles get deposited on the substrate. The next one is magnetron sputtering. This technique involves strong magnetic field resulted in a magnet or coil placed in the target holder unit. The ion sputtering is concentrated on the target with the help of magnetic field by electron pathway. Since the ion sputtering is concentrated over a specific domain, it ultimately results in higher deposition rate and larger deposition area. Electroplating is an electrolytic method in which the substrate and the coating material act as anode and cathode, respectively. This method uses electric current to minimize the number of ions in the electrolytic solution so that the amount of material deposited over the substrate is controlled continuously. This method results in good coating growth speed with uniform thick film deposition. Atomic layer deposition. This technique involves gaseous chemical precursors that react with substrate in an alternating sequence. At every sequential pulse, a reaction occurs between the precursor and the substrate surface, thus forming a thin film over the substrate. This sequential pulse is continued until the desired thickness of the film is achieved. The coating formed are very durable and reliable even at low temperature. Spin spray. It involves the precipitation of solution over a heated surface in order to produce a thin film. It is a technique used for depositing thin films of selenide and sulfide. The main apparatus required in this technique is a surface heater which atomises the solution. Another technique is cathodic vacuum arc deposition. In this method, electric arc causes the material to vaporize and stream towards the target substrate to get deposited in the form of thin layer. The deposition process can be made reactive by adding nitrogen gas in an argon plasma. Dip coating is one of the simplest and easiest method used for coating a substrate. The substrate is submerged in a vessel filled with liquid solution. The main benefit of this method over other is that it is economical and reproducible. This method is capable of producing the thin, thermally stable film with a uniform composition throughout the surface of the substrate, offering better spectral selectivity. Now, coating method and characterization techniques. Now, again, you will see that we have different authors, the year in which they have done their work, the selective coating which they have used, the coating method was electroplating, the characterization is spectrophotometry, and what is the outcome is the reported absorptivity and the emissivity. So this is the different authors or different researchers who have worked over the years with different type of selective coatings, different methods they have used, and accordingly they have been producing what is called as a the outcome about the absorptivity and the emissivity. This is, you see, up till 2018, we have different techniques being used. 2019. Okay. Base material in the selective coatings. Now you see that the different base material which we use, they are like silicides. We have a black chrome based, and we have mostly these coatings, they are aluminum based, that is 50% of them. Here the figure represents the base materials taken by the researchers worldwide. According to the study, 32% of the high temperature fluids are made by taking silicides as base fluid. 18% are made by taking black chrome as base material, while 50% of the high temperature fluids are made taking aluminum as the base material for the selective coatings. Now the conclusions are, the performance of the system depend primarily on parameter like heat transfer fluid, the available heat flux, collector area, and optimal performance of the system. Nanoparticle based heat transfer fluid, especially metal oxide, they offer better thermal characteristics. Selective coatings can encounter corrosion at high operating temperature, hence some anti-corrosive agent like graphene nanoparticles need to be integrated to retain their optical behavior. The coating material should possess requisite optical properties depending upon the type of application. Copper, chromium, manganese, oxygen, aluminium, molybdenum, aluminium layer are and maximum absorptivity. So this is based on the literature review which we have done. Coating deposition method seems to have an immense significance with regard to even deposition of the film over the substrate and its environno-economic potential. So these are the various references which we used. These are basically very brief list is there because we have a elaborate list where we referenced around about 200 journal papers for arriving at these conclusions and getting our material developed. Thanks a lot for a patient hearing.
Thank you so much, sir, for such a beautiful and lovely talk. We gained a lot of knowledge and enjoyed your presentation. I hope all the participants get benefited from this. The advantage of chances for opportunities do not always occur at will. What is there now may not have appeared yesterday and may disappear tomorrow. Now, finally, I would like to invite Engineer Anamika, Coordinating Committee member, for the final vote of thanks.
Thank you, Azli ma'am. I'm audible?
Yes, ma'am.
Okay, thank you. A lovely and warm afternoon to our most valuable and worthy guests, respected faculty members and participants. It is a matter of pride for me that I am proposing a vote of thanks for third day of FDP. I, on behalf of Electrical Department and entire Ycet College, I want to thank our speaker of the day, Dr. SANJEEV Anand, Assistant Professor, School of Energy Management, SMVDU, KATRA, who delivered his talk on thermal selective coating and its enhancement characteristics for efficient power generation through parabolic trough collector. Thank you very much, sir, for ignoring your necessary work and sharing with us your sagacious knowledge. Thank you very much, sir. Also, I would like to thank Dean Ycet, Dr. Dinesh Gupta, Chief Coordinator, Engineer B.R. Verma, sir, HOD Electrical Department, Engineer Lavnish Talwar, sir, Coordinating Committee members and technical teams. Last but not least, I would like to thank our participants and thank you, everyone.
Thank you, Sanjeev sir. You devote your precious time, you spare the precious time for us and to become the part of this FDP program. Thank you again, once again, Sanjeev sir, for your lovely, beautiful talk. Also, thank you so much, Dinesh sir, Dean Ycet, that he also spare his time and become this part of this FDP program. I would also like to thank B.R. Verma sir, Chief Coordinator Ycet, for joining this event. Thank you so much. But most important, again, as Nabika has already told, all the participants who have joined this session. So this is about the third day of FDP program. Now I request all the participants to please turn on your videos so that we have one group photograph. I request all the participants to please turn off your videos for a short while so that we can take a group photograph. Just a minute, we will take, click. Yeah, thank you so much. Thank you so much. It's done. So once again, on the behalf of entire team of Yogananda College of Engineering and Technology, I love Nish Talwar, head of the department. Thank you all. Special thanks to Sanjeev sir. Thank you so much.